We're filling a bucket with water, and that creates a related rates problem. Related rates problems arise when you have multiple variables that all change with respect to some other variable. Usually that other variable is time, and it is in this case too. As we fill the bucket with water, the volume changes with time, the height changes with time, and the radius of the top layer of water changes with time. The shape of our bucket is a frustum. It's a cone with the tip cut off. And so the volume of that shape is given by pi over 3 times the height multiplied by the big radius squared plus the little radius squared added to the product of the radii. Our bucket has a base with a 9-inch radius. And the bottom of the bucket doesn't change. It stays 9 inches. However, as we pour in the water, the height of the water increases as well as the radius of the top layer of the water. So both the height and then the top radius is increasing. The volume is also increasing. So our formula that then relates volume to height and radius for this bucket would be pi over 3 times h times the quantity r squared. 9 squared is 81, and then we want to add 9 times the big radius, because again our little radius is set at 9. We then want to take the derivative of both sides of the equation. Note we're not plugging in any known values because we know that all the values change with time. So if you are given a problem and you have multiple values in the problem, make certain that you only plug in ones that stay set the entire time. So in our case, the 9 inches stays fixed the entire time, but all of the other variables change. So you want to leave them as variables. So the derivative of the volume will be just dv dt, the rate of change of volume with respect to time. And then I have a product here. I have a first function involving the height, and then I have the second function involving the radius. So taking the derivative, I have to do the product rule. So I leave one function alone, and then I multiply by the derivative of the other function. So power rule 2 times r, chain rule times dr dt, because the radius is a function of time. The derivative of 81 is 0, so it's not going to appear. It'll turn into a 0. And then the derivative of 9r will be 9 times dr dt. Then I add to that function left alone multiplied by the derivative of the first function. So notice before I left pi over 3h alone, I'm now taking the derivative of that, and we get pi over 3 times dh dt. So I now have a formula that relates all of the rates of change. Suppose we knew that the water was pouring into the bucket at 122 cubic inches per second. So I replace dv dt with 122. And then suppose at a certain moment in time, we know that the height of the water is 8 inches when the big radius, that's the top layer of water, is 12 inches. So I can replace the h with 8, and any place that r shows up, I can replace that with 12. And suppose we knew that that radius was increasing by 0.1 inches per second. Then the dr dt can get replaced with 0.1. So I replace all the known values, and the one value that's left unknown is dh dt. So I want to solve for how the height is changing with respect to time. So cleaning this up, 2 times 12 is 24, but 24 times a tenth is 2.4. And 9 times a tenth is 0.9. And then 12 squared is 144. 9 times 12 is 108. If I add 2.4 and 0.9, I get 3.3. And if I add 144 to 81 to 108, I get 333. I can also divide 3 into 333, and that gives us 111. So if I'm trying to solve for dH/dt, I want to subtract this value. When I do, 122 minus that value gives me 94.354. So that equals pi times 111. I'm trying to solve for dH/dt, and dH/dt is being multiplied by pi times 111. So last step, divide by 111 times pi, and that gives me a rate of change of height with respect to time of 0.271 inches per second. Notice the units are inches per second because the volume was cubic inches per second and my radius was inches. So by the time you look at the units, you'll see that we get a change of height of a little bit more than 1/4 of an inch per second.